Welcome back, and now we're going to take sequences a step further and look at limits, because again, one of our first studies in calculus was the idea of limits. So now calculus formally is really the study of change, so how things change. And so we want to look at a sequence and see how that changes, and that's where limits come into play. Okay, formally, we would say a sequence has a limit if we can write that it converges, or so that the limit of the nth term as n goes off to infinity is L, and then you could also just write it using this sort of notation as well. Also, I want to say that L is finite, okay, meaning we typically don't say it's infinity. Okay, and then really all this means formally is that as we increase n, we get close to L. And when we talk about that L number existing as a finite number, then we would say that the sequence is convergent, otherwise it's divergent. Okay. Now, this next definition, this is going to be a little bit of a foreshadow for Calc 2. Same idea in terms of the definition of a limit, but now this next bit here, this for every blah blah blah, that's new to us. But this just says for every epsilon greater than 0, there's a corresponding integer n, such that if we look at the distance, okay, absolute value means distance, if we look at the distance between the nth term of the A sequence and our limit L, that's less than epsilon, and epsilon, again, I can make it any number that's positive, okay? But so and this is saying I get really close to L whenever I'm at this number, which is fixed, or above, okay? So when we look at these as diagrams, okay, the first one, more generally speaking, we're going to have an axis where we have n and then an, this should be our an axis, and then this is our L. So then what we see happen over time is something like this, boom, 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 and we're going to kind of asymptote to L. Imagine that's a straight line, okay? And certainly these are like 1, this is 2, this is 3, and so on and so forth. Okay. Now the second diagram, that one's a little bit more interesting. We still have the same sort of axes set up. We have n, and then we have our an axis. We still have L, so I'm going to draw that dashed line in there first this time. Okay. And now what I'm saying is that when I look at the sequence, so I have my same sort of sequence approaching L, right? It says once I am beyond this position in the sequence, capital N, okay, what I'm looking at is this vertical distance, because this vertical distance, that's our an minus L. And I'll take the absolute value of it. So I look at this vertical distance, the difference between an and L. Okay, and I'm looking at it all the time. But it's saying that once I'm beyond this place in the sequence, right? If I look at this distance, so this distance right here, it's very, very tiny. This distance, so that an minus L, is going to be less than whatever epsilon I choose. So it's pretty close, okay? That's the idea with the formal definition of the limit, okay? So we have this idea of a limit, okay, and now we want to be able to find the limit, right? We can say, oh yeah, it's, there is a limit, we want to be able to find it. So just looking at an example here, we want to determine whether the sequence is convergent or divergent, and then if it is convergent, find its limit. And so how do we do this? Well, don't we kind of remember, okay, so imagine that this was like saying f of x is equal to x plus 1 over 3x minus 1. Didn't we, when we looked at the limit as x goes to infinity of f of x, didn't we just say that, oh, that's a rational function? So there were various ways of thinking about this. I believe Professor Keenan uses the idea of big potatoes and small potatoes, and they're equal sized potatoes in this case for x and 3x. So the limit ends up being 1/3 if we look at the function rate. But now we're looking at a sequence where n is within the set of, actually, no, not integers, natural numbers. So we're only looking at, counting numbers 1, 2, 3, 4, da 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 da. Nevertheless, the limit is still going to be 1/3 as we go to the end, because all we're doing is picking off values at certain increments, right? So this one ends up being 1/3 for this limit. So this is going to be convergent. And then I'm just going to say limit of an as n goes to infinity is 1/3. And I should probably define that as an. Whoops. Okay. And so really to find the limit, the same mechanisms that we use to find limits of functions works. And that's really what this last theorem is saying. Because if we know that the function has a limit of L, then the sequence, the corresponding sequence, if we view the function as just, again, kind of the integer values from the function, then the limit of the sequence is going to be the same as the limit of the function. So, formally, if we want to look at this in a diagram, okay, again, this would be x, and this would be f of x, okay, we could see maybe the function has this sort of behavior. I'm just going to model something. Okay, so we have something like that, and then we look at L as being kind of this long-term line, okay? And we're just going to ignore that little error message that came up. It doesn't much matter. But anyway, what I'm doing here with this function now to illustrate this above theorem is that here's the function f of x in blue, and all I'm going to do is say pick off the integer integer value. So this would be like 1, this would be 2, 3, 4, and then so on and so forth, right? And I'm looking at just the integer values as we go off to infinity, and they end up approaching the same value. So that's kind of illustrating the above theorem. Okay, and consequently, now that we have we've connected the idea of limit of a function to the limit of a sequence, all of our limit laws that we had back from functions apply. And so this is just an image from the textbook illustrating all those properties. So review them as needed, and then we're going to move on and actually get some practice with finding limits.